Hello everyone. Today I'll be doing our open response problems for section 10 on series and sequences. Um, and these are our three open response problems starting with 10.2, 10.7, 10.8, and the open response problems that we were assigned. So I'll start this problem. When I'm looking at convergence tests, the first thing I notice with this problem is that both of these bases that are raised to an exponent are raised to the nth exponent, which makes me think that we're going to be doing the root test for this problem. And if you don't remember the root test, it is simply the limit as n approaches infinity of the nth root of whatever your function is. In this case, that's this. I'll just call it a of n. And for this, if it's less than 1, then it's convergent. And if it's greater than 1, we know it's divergent. If it equals 1, then the test fails, and we have to do a different test. But as soon as I see those n exponents, I immediately think that we'll be using the root test. So before I start doing that, I want to get rid of this negative exponent because that makes it kind of ugly and harder to deal with. So instead of having the negative exponent, that's just the same as 1 over 3 to the n, which means I can change this infinite series to be 2 to the 2n over 3 to the n. And when I do the root test, as I just shown before, I will be doing the limit as n approaches infinity of the nth root of 2 to the 2n over 3 to the n. And these n's will cancel out. The nth root cancels out with these n's. These exponents will all be taken away, which means this limit becomes the limit as n approaches infinity of 2 squared over 3, which equals 4 over 3. Now, as I talked about before, with the root test, if you get a limit that's greater than 1, which this is greater than 1, then we know it's divergent. Divergent. Sorry for my awful writing. But this problem is divergent. Okay, so now we're going to move on to this next problem. And this part of the problem here, I underlined it because this integral part looks kind of scary. But we can ignore it for now. And actually, we won't ignore it for now. We will do that initially. It just adds one extra step. So it seems kind of scary, but all we have to do is take the integral of this function first, and then find the integral of convergence. So I'm just going to rewrite f of x, this infinite series, infinity and n equals 0, of x over 3 to the n. And so we're going to take the integral of this. And it's the integral with respect to x. So what we notice is this is just a power rule integral. So remember, if we're taking the integral of, let's just say, x squared, then with the power rule of integrals, we add a 1 to the exponent and then divide by this new exponent, which 2 plus 1 is 3. And so the integral of x squared is going to be x cubed over 3. And then in order to check to make sure that's right, we take the derivative, and we know with the power rule, we just subtract 1 and multiply. So times 3, the whole thing, and those 3's will cancel, and it's just x squared. And so that's how we know it's right. So if we look back at our first step, all we did is took the exponent, added 1 to it, and then divided by that new exponent. And so we just have to apply that rule more generally to our infinite series right here. And n is our exponent. So this integral is going to become the series from n equals 0 to infinity of x over 3 to the n plus 1, but divided by n plus 1. And so this is our new function. And instead of having these double fractions, I will rewrite this to make it less confusing. I'll rewrite it as x over 3 to the n plus 1 times, times 1 over n plus 1. And so now all we have to do is find the interval of convergence. To find the interval of convergence, we'll do the ratio test, which, if you recall, is we will just plug in n plus 1 for every value of n, and then divide it by the original. And then if that value is less than 1, it's convergent. And so in order to find the interval of convergence, we're going to find all values of x that make it less than 1. So I will start this ratio test with, and it's the limit as n approaches infinity of x over 3 to the n plus 1 times 1 over n plus 1 plus 1, and then all over x over 3 to the n plus 1 times 1 over n plus 1. So this simplifies to limit as n approaches infinity of x over 3 to the n plus 2, which I will rewrite as x over 3 to the n plus 1 times x over 3, and then times 1 over n plus 2, which is over x over 3 to the n plus 1 times 1 over n plus 1. And we'll notice these factors cancel, and we end up with x over 3 times 1 over n plus 2 over 1 over n plus 1. And the limit as n approaches infinity, all we care about when we do these limits as n approaches infinity is the leading coefficients of the factors of n that have the greatest valued exponent. And both of these have a negative 1 exponent. They're both, that's why it's 1 over n plus 2. It's a negative 1 exponent, which is the greatest for both. Which means that we only care about their leading coefficients, and since they're both 1, they actually cancel. So we can only cancel these when we're doing the limit as n approaches infinity, because they have different denominators. They're not actually the same number, but we can when we're doing limits. And so these two will cancel, which means we get our answer is just x over 3. So I will undo, or actually this is faster. I'll give us more room and I'll rewrite. I'll say our answer was x over 3. So now we want this to be, the absolute value of this to be less than 1, which means we can write this inequality where negative 1 is less than x over 3, which is less than 1. And we solve this inequality by multiplying by 3, and we get negative 3 is less than x, which is less than 3, and that is our final answer. That's our interval of convergence. Okay, next problem. So let f of x equal 1 over 1 minus x squared. Find a power series centered at x equals 0 and find its interval of convergence. Okay, so for these problems, we must know kind of the general rule for finding power series, and this stems from geometric series. When you have an infinite sum like this as n equals 0 of a, which is going to be a constant, and then r is our rate, to the n. And this series equals 1 over 1 minus r. And this is a convergence series, and this is true for when r is less than 1. So that's when this is true. So what we're doing is, instead of going from the series to the this value, we're going to go from this value to the series. So we're going to kind of work backwards. So basically what we're going to try to find, and sorry, actually this value is a over 1 minus r. Sorry, that's the most simple term is when a is 1, but a can be anything, so it's a over 1 minus r. And so we're going to work backwards from this to get this power series. So we can see, I'll leave this up actually. Well, our goals are going to be to find a and to find r. So for this one, our function is 1 over 1 minus x squared. So our problem is that this bottom part is squared, which makes it different from our general formula that we're trying to find. So we can rewrite this. When you have a problem like this, you want to get this form at all costs. And so what we can notice is that this is 1 over, or it's technically just 1 minus x to the negative 2. And we want to get it so it's kind of, if x is r, or the value of r we're trying to look for, we want it to just be 1 minus x to the negative 1. That's what's over here. This could be rewritten as a times 1 minus r to the negative 1. And since a can be any number, that's what we're looking for. And so to get from here to 1 minus x to the negative 1, or something times that, we can take the integral. So if we take the integral of 1 minus x to the negative 2, we get, I'm going to write this d over dx here, which basically means that whatever, this is going to be the integral of this, of 1 minus x to the negative 2. So when we take the derivative of whatever we put over here, we're going to get back to that. So we want to keep this here so we know it's all equivalent. And we're going to have to undo this part later on, and you'll see what I mean once we get there. But using the power rule, we can add 1 to this, power rule of integrals, and then divide by negative 1, which is what we get there. So we end up with 1 minus x to the negative 1 over negative 1. And it's the derivative of all that. So this could be rewritten in the form that we were looking at earlier, which is d over dx of negative 1 over 1 minus x, which now fits this general rule. And so we can change this. What we're now going to do is we're going to keep the d over dx, that's very important, of this infinite sum, n equals 0, of a, which a is negative 1, times r, which is just x, to the n. And so now we just bring this derivative in with respect to x, which means we end up with this sum of negative 1, and we just do the power rule. So negative 1 times x to the n minus 1 times n. And this is our power series that we're going to use for the rest of this problem. So now we have to find the interval of convergence of this, which means we're going to have to do the ratio test, as we did in the problem before. And so this ratio test, I'll start over here. This ratio test of the power series we just got is going to be negative 1 times x to the n plus 1 minus 1, which is just going to be x to the n, times n plus 1, and then this times 1 over negative 1 times x to the n minus 1 times n. So we can rewrite this First of all, we can see right off the bat, these negative ones are going to cancel. So this is going to equal the limit as n approaches infinity of x to the n times n plus 1 over x to the n, and we have this x to the n minus 1, which, as we remember, x to the n plus 1 would just be x to the n times x. So this is going to be x to the n divided by x, and since it's on the bottom, that x is going to come to the top. So times x, and then times n on the bottom once again. And these x to the n's will cancel. And once again, as we talked about before, as we're doing this limit as n approaches infinity, we can cancel out these two terms as we only care about their coefficients. And we get our limit is x. So, using the ratio test, we know the interval of convergence is -1 is less than or equal to x is less than or equal to 1, which in this case, we already have x by itself, so we don't need to solve for anything, and this is just our interval of convergence for the power series. And that is all of our open response questions for section 10. So I hope you were able to use this to study and to learn a bit about what infinite series are about. Thanks for watching.